Notes 13.3, and it's just this Hardman coming to you live from Whiting, Indiana. So anyway, book connections. Someone's been looking for the book. Can you tell who? Make sure to read these sections and do 2 self-checks. I think you'll be happy that you'll be able to do them after this. All right. So here we go. Water's wet. Oh yeah. And since it is, there's some H2O, H plus, and OH minus. We did this in class. H2O liquid hits the other H2Os and turns into hydronium and hydroxide ions. So because every time you get one of these, you get one of these, then you have equal amounts of H plus and OH minus. So that means our KW is on the next slide. So here are some equations, and you need to know them all. Okay? So anytime you take the negative log of a concentration, you're getting whatever the concentration you put in, you're getting the P of that. Okay? So P whatevs is the negative log of whatevs. So make sure that you know which one you're using. Now, what if you have the pH and you want the concentration of the ion? Then you have to plug in 10 to the negative pH on your calculator, and that's going to give you the molarity. Okay. Now, if you plug in pH, you get the hydroxide. If you plug in POH, you get the, I said hydroxide, hydronium ion. If you plug in POH, you get the hydroxide concentration. Here's something. pH plus POH equals 14, and we already know that pH equals 7. If we did negative log of the POH, we'd get 7. That's why pH plus POH equals 14. Okay. All right. What is the pH scale anyway? It's how acidy is your acid and how basey is your base. Sounds like a fun song, but just to give you an idea of a few kinds of pH. Okay, so you got your vinegar, weak acid. You got your hydrochloric acid, strong acid. Ammonia, weak acid. Sodium hydroxide, I said acid. Oh, golly, base. And then drain cleaner is NaOH. And that's a base. And then you got your water and your baking soda, which are closer to the middle of the pH scale. So they have closer to 10 to the negative 8th molar hydronium ion or hydroxide ion. Well, this is hydronium ion. pH is all in terms of hydronium, which is hydrogen ion. So where does it come from? All right, if it's a strong acid, the hydrogen ion concentration is the total concentration of the H plus. Why? Because that's where it came from. HCl breaks up 100% into H plus and Cl minus. So if the concentration of this was 5 molar and it all breaks up, we lose 5 molar of that and have 0 of that less, and now we have 5 molar of that. Okay, so what is the pH of a 0.004356 molar HCl solution? Well, here we go. Acid or base. Acid, strong or weak? Strong. So the pH has to come from the H plus. So the hydrogen ion concentration is 0.00356 because all of this turned into H plus. So then you do negative log of 0.00356, and you find out that the pH is, I gotta get on the right page of all my practice stuff, 2.45. pH is 2.4. That's an acid. You betcha it is. Okay. Well, what if it's a strong base though? Well, then the total concentration of the base is the total concentration of hydroxide. Same reason. I'll give you this again. NaOH, Na plus OH minus. If this was 5 molar and it all dissolves, then there's none of that left, and we get 5 molar of that. So the pH, though, you have to be careful. If we take the negative log of this number, then we're taking the negative log of the hydroxide. So that's not pH, that's POH. Whatever you take the negative log of is what you're getting. So then that is negative log of 2.45 times 10 to the negative third. And you get the POH is equal to 2.61. Now from that other slide, we found out that pH plus POH equals 14. So pH equals 14 minus 2.61. So the pH of that solution is 11.39. And that's basic. Okay. So if it's a base and you take the negative log of it, you're getting POH. If it's a strong base, This is that. Okay. pH. Give the pH of the following. All right, so it's 0.15 molar H2O for weight. Acid or base? Acid. Strong or weak? Strong. So that means this is 0.15 molar. So then the pH equals the negative log of 1.5 molar. And that is 0.82. Negative log of 0.15 equals pH equals 0.82. Okay, now here straight up it's telling you the hydrogen concentration. So hydrogen ion concentration. So you have to just take the negative log of 2.50 times 10 to the negative fourth. And you find out that you get 3.60, pH of 3.60, and that's an acid. So is this. Okay, which has more hydrogen ion? This one, it has 0.15 molar. Okay, find the pOH of the following hydroxide ion concentrations. So if I tell you the concentration of NaOH is 1.5 times 10 to the negative third molar, then you say to yourself, self, acid or base? Base. Strong or weak? Strong. So the hydroxide concentration is 1.5 times 10 to the negative third molar. So that means that the negative log of that is going to be what? Careful here. This is OH, so this is pOH. Whatever you take the negative log of, you're getting the P of that. All right, so that is 2.82. All right, and that's what you were looking for, pOH. pOH equals 2.82. So stop right there. Oh, look, it's the hydroxide concentration straight up. Negative log of that is the pOH. Negative log of 0.001. Hey, that's 1 times 10 to the negative something, so I already know the pOH is 3. Right? You could just, if you can do that. Now, that's the pOH. That's the pOH. Okay, but what does that mean about acid or base? We always do acid based on pH. And up here we found pOH to be 2.82. Well, 14 minus that is the pH. So 14 minus that would be basic. Okay, so this is the base. And then pOH of 3 means pH is 11. So then this one would be pH equals 11. So that's a base as well. All right, so you could do acids and bases based on pH or pOH, but let's just stick with pH. Low pH is acid, high pH is base, 7 is the cutoff. All right, so that gives the pH following, given the following pOHs. Whoops, sorry. Give the pOH given the following pHs. That's a little backwards, but you see if this is pH, then pOH equals 12. pH equals 11, pOH equals 3. Why? Because those have to add up to 14. Remember, pH plus pOH equals 14. Okay, it's all about logs. ID is acid or base. Well, if the pH is 2, it's an acid. If the pH is 11, it's a base. You don't have to know pOH to do acid or base. Find the hydroxide given the pH. All right, so we want to do something different here. We want to find hydroxide concentration. So it's easiest to change that, 3.22, into 10.78. How do I do that? I used they equal 14. So then to get the hydroxide ion concentration, we have to say 10 to the negative 10.78. Okay, and so that's going to give us 1.7 times 10 to the negative 11th molar hydroxide ion concentration. Okay, it's just easier to do hydroxide ion concentration if you know the pOH. So in this case, pOH equals 4.67. Remember, these add up to 14. They add up to 14. These add up to 14. So then, if I want hydroxide ion, I need to take 10 to the negative 4.67. This is the caret to plug into your calculator. So I find out the hydroxide ion concentration of this one is 2.1 times 10 to the negative 5th molar. All right. Same thing but different. We want hydrogen ion. We're given pOH. So find the pH first. That's 11.85. Okay. So then the hydrogen concentration is 10 to the negative 11.85 is 1.4 times 10 to the negative 12th molar. Hey, does that make any sense? Well, it sure does. if the pH is 11.85, then we're talking that it's pretty basic, so we should have not a lot of hydrogen ion. Okay. In this case, if the pOH is 12.6, then the pH is 1.4. And so then the hydrogen ion concentration is 10 to the negative 1.4, and we get 4.0 times 10 to the negative second molar. Does that make sense? Well, yeah, this is a very acidic pH, right? So we should have a lot of hydrogen ion concentration. All right. You can do anything now, all right? This time we're working with hydrogen ion. Oh, we want to find hydroxide ion concentration. We're given hydrogen. So the other formula we know is that 1.0 times 10 to the negative 14 equals the hydrogen ion concentration times the hydroxide. That's our Kw. We can assume it's 25 degrees. So if we want this, then we could take 1.0 times 10 to the negative 14 over, we want to find this, then we would, the hydroxide ion concentration would be this, times 10 to the negative 4th. All right, so I just put that in there, solve this equation using 1 times 10 to the negative 14th, and I get, for hydroxide ion concentration, 1.58 times 10 to the negative 11th molar. Okay, and I went with 3 because of 3. All right, now I have hydroxide. I want hydrogen ion concentration. All right, so then I say 1.0 times 10 to the negative 14. That's our Kw is equal to this. So see these formulas? Write them down. Write them down every time, and then use them, and I'll see what you're doing with them, so I know what you're doing. All right, so then I just need to divide by 0.195. And I get the hydrogen ion concentration is 5.13 times 10 to the negative 14th molar. All right, so can you just by looking tell if it's an acid or a base? Well, this is going to be a base because the hydrogen ion concentration is very low. Okay. All right, so that was easy enough if we know H plus or we know that's a strong acid or strong base. What if the acid or base is weak? All right, well, let's see what happens. What is the pH of a 0.242 molar acetic acid solution? HC2H3O2. Is that so? Acid or base? Acid. Strong or weak? Weak. Then we have to do an equilibrium equation because we know that not all of the H plus is going to come off of this. All right. So then we know we have H plus, which is aqueous. And we know we have C2H3O2 negative, which is the acetate ion. It's aqueous. So we do an equilibrium expression for it, and we'd have hydrogen ion concentration times acetate ion concentration. Hey, did I say put the charges? Because you got to put the charges. Over the concentration of the acetic acid. Now, why is this aqueous? Because all of this is surrounded by water. And not all of this turns into that. Okay, so here's what we're going to say. Initially, we have 0.42 molar acetic acid and 0 hydrogen ion concentration and acetate ion concentration. It's going to change. Some of this is going to dissolve. We don't know how much. Or dissociate. We don't know how much. But every time one of those breaks up, we get one of those and one of those. So at equilibrium, we're going to have 0.42 molar minus X. It's going to be X over X. All right. Now you're saying to yourself, wait a second. I need this to find pH. So how do I solve for that? Well, that's going to be X. So then we would plug it in, and we'd have X times X over 0.42 minus X. But we have to set that equal to something. So is there something we could set it equal to? Yes. We have what are called Ka tables, and we are looking at acetic acid, and we find out that its Ka from this Ka table is 1.8 times 10 to the negative 5th. So we can say 1.8 times 10 to the negative 5th. Now, if we solve for X, we can use a quadratic formula because we'll have X squared, we'll have this, we'll have to bring it over. But wait, there's a little trick we can do. See this exponent here, that's the negative 5th. See this is to the negative 1st. They're within they're about 5 orders of magnitude, 4 orders of magnitude apart. So the truth is that this X is going to be really small because this is a weak acid. So we can assume X is small, assume small enough that if you subtract it from 0.42, it's not going to matter. So now we really have 1.8 times 10 to the negative fifth times 0.42 is equal to X squared, and then we square root both sides, and we find out that X is equal to 2.75 times 10 to the negative third molar. Okay, so you multiply that times that and square root it. So what does that mean? Wow, we did a lot of work, but now we know the hydrogen ion concentration at equilibrium. Okay, so I'm going to go up to the top of the page and look at what they asked. What is the pH? We did all this work to find the hydrogen ion concentration because we knew not all of that dissociated. So then we could say the pH is going to be equal to the negative log of 2.75 times 10 to the negative third. And so pH equals 2.56. All right. But the reason we had to go through all of that is because this is a weak acid, and so not all of this turns into H+. Okay, you could only assume the molarity of the acid is the H+ when it's strong. Here is a Ka table. You'll get these if you need them, or this will be given in the problem. Okay, so what's the difference with the base? Well, there isn't much difference, but just a little. So here's some weak bases. How can you tell they're weak? Look at these values are small. Okay, what does this value mean? It's the equilibrium constant for a base. So it's products over reactants for a base, and if it's really small, that means that the product side is not favored at equilibrium. The reactant side is. Okay. Hey, it's a weak base. Okay, so let's see. Calculate pH. All right. In order to calculate the pH, you need the H+ ion concentration. All right. What do we have? Given N2H2. Wait a second. That's a base, and it's weak. How do I know? Here it is. Hydrazine. Hey, we talked about hydrazine. You guys told me how toxic and poisonous it was. Okay. So its Kb value is 1.7 times 10 to the negative 6. So we need an equation to get that Kb. So we start out with the N2H4, and it's going to react with water. Now, these ones you have to show water because they don't break apart into ions the way acids do. You don't just give off an H+. This has to take on an H+. So we spent some time doing this. It's going to turn into 5 H's with an extra plus sign. This is all aqueous. This is liquid. This is aqueous, because this is surrounded by water, and so is that. And then we get some hydroxide ion concentration. Okay, we're getting closer to hydrogen ion concentration, but we're not quite there yet. All right, so Kb is products over reactants, so we have N2H5 positive and OH minus over N2H4 hydrazine. All right, the Kb, we looked at that table, is 1.7 times 10 to the negative 6, 1.7 times 10 to the negative 6. And now we need an ice table. Initially, we have 0.35 molar of this, and none of that and none of that. That's going to change. By what? Some of that's going to go away, and every time that happens, we'll get one of those and one of those, because the coefficients are 1s, right? And then, so at equilibrium, we're going to have 0.35 molar minus x. It's going to be equal to x times x. So let's plug it in. We have x squared over 0.35 molar minus x. Now, this is to the negative 6. This is to the negative first. That's a big difference. That's like 5,000, not 5,000, 10,000 times different, right? An order of magnitude of 5. So we can assume this is small and not use it when we're solving. Okay. So then this is going to be 1.7 times 10 to the negative 6 times 0.35 is going to be equal to x squared. So then you square both sides and you get, let's see what I got. See, I practiced these ahead of time for you guys. I get 0.000, what the, 771362 is equal to x. What does that mean? Well, that means X, if I go back and look for X, X is hydroxide. So that means the hydroxide ion concentration at equilibrium is 7.71 times 10 to the negative fifth molar. All right, am I done? Not even close. Why? Because in order to find pH, we need H plus, but right now we have OH minus. So we get to choose. What do you want to do? Do you want to use the KW to figure out H plus and then figure pH, or do you want to take the negative log of this and subtract it from 14? You can do it either way. So I'm going to take the negative log of this and get 3.11. But I'm not done yet because that's POH because I negative logged that. So then pH finally is equal to 10.89 because this plus this had to equal 14. The pH is 10.89. Wow, it's a lot of work, but at least you've seen it once here for each of the weeks, a weak acid and a weak base. You see that you could drop out the X because if there's a big difference between this and this, then subtracting off. If I subtracted off this number from this, it wouldn't even change it very much. Okay, so that's why we can assume that's small. And that's the calculations for this section. So the other thing I want to talk about was indicators, litmus. And we talked about litmus. So how does it work? I'm glad we did this equilibrium stuff. So litmus is a weak acid and has a very complicated chemical formula. So we'll just call it H-lit. H for acid, lit for the rest of it. Right? The H is a proton that can be given away, and the LIT is the rest of the weak acid molecule. So it's the negative ion. Now this is red, and this is blue. The two colors of litmus, right? Red and blue. And it's an equilibrium system. All right, so let's think about why it changes colors in acids and bases using Le Chatelier's principle. What if I add an acid to this? Okay, well, this one says, okay, so if I add acid, then I'm adding more H+. More hydrogen ions means more H+. More H+ would stress out this side, so what does the equilibrium do? It shifts to red, blue to red acid. All right, let's think about the other way. If I had hydroxide ions are OH minus, the OH minus would go and grab the hydrogen out, all right, and then it would shift towards blue, okay? So indicators work by shifting equilibrium based on the properties of the indicator and the colors they are. Let's try it one more time. Hey, it's phenolphthalein, spelled right. Ooh, spelled right, yeah. Okay, so here's the H. So this is the acid form of the phenolphthalein. This is the ion form of the phenolphthalein. Oh, look, it's two different colors. Okay, so here's your pink and here's your clear. Okay. So what would happen if we add acid? We add acid, then we're adding H+, more H+, stresses that, so it shifts to there, go clear. Go clear. If it was already pink, it would go clear. If it was already clear, it would stay clear. Okay. If you add base, you're adding hydroxide. Hydroxide and hydrogen. Hydroxide pulls it out like, come with me, I'm hydroxide. Come here, hydrogen. So if hydrogen's going away, then that stress, then this rate goes faster, pushes towards that way, and it'll go pink. All right. So indicators are equilibrium-based reactions of weak acids. Okay, so your phenolphthalein is actually a weak acid. Here's its clear form is the acid form. Its pink form is the ion form. Okay, look at all these indicators. We did a lot of these on Friday in the lab, right? And you can see that their acid form, here's the colors they are, right? And then their ion form are those colors. And you can see not all of them equally spread out their colors at pH 7, okay? Methyl violet is violet in most pHs, but it is yellow and kind of greenish blue in some at high pH, okay? So, I mean low pH, 1 is a low number. Okay, so to review, calculators rock, woo! And so you get to use yours, but you got to know how, all right? And so to know how, you have to plug stuff in, right? Memorize formulas. All right, woo, woo, woo. Indicators are colorful and use Le Chatelier's principle. pH is actually used in real life to diagnose problems. Check in your swimming pool, see if you have a blood poisoning, certain crops, antacids, acid rain, it's everywhere. So, if you think you got this, which I hope you do, practice 16.3 and 16.7 self-check, and remember that those answers are found in the back, so you can check your work of what you did. Alright, peace out. One more video notes after this, so enjoy it. Hope you learned something. Come back to it if you need help, and I'll see you soon.